Good morning, everybody. The first speaker today is Piotr, Sołtan, who will speak about quantum spaces, which are not quantum groups. Please, the floor.
Thank you. But yes. Thank you very much. Let me thank the organizers for, first of all, organizing this meeting and inviting me to it. I was, in a way, faced with the topic given to me. This is some old work that I've since, well, improved on and gone further. But in any case, this is going to be a talk based on my joint work with Jacek Piotr. Yes, as a first item on the agenda, let me say that the whole talk represents really my failure to understand graph algebras well enough to use their structure to prove statements that will come up, because I actually tried to do it knowing that certain algebras were graph algebras, but then I had to do it in another way because I couldn't use the graph algebra structure somehow. I wasn't clever enough.
Like Frank Sinatra, you did it your way.
Well, okay. So the plan for the talk is the following. I will pretty much repeat some of the things that were already said, the basics of non-commutative topology, and this will include a very brief discussion of what a compact quantum group is, because I know that not everyone here is well acquainted with this notion. And then the bulk of the talk will be this part, which is just in a way it is an exercise that will show that the quantum disk cannot carry a quantum group structure. Later I will, but very briefly, I will just tell you about some results that are in the same vein, but not exactly the same, slightly more general. And at the very end, I will maybe tell you a little bit of the more recent developments, which actually, in a way, follow from that original exercise in point 2. So I think I didn't forget anything. So let's just start with this. So this notion already appeared in pretty much the same language. So we are using Gelfand's theorem for commutative C-star algebras as the basis of defining the notion of a quantum space. So a compact quantum space is an object of the category dual or opposite. There are, I guess, different names for the same thing, to the category of C-star algebras. And this compactness here corresponds to the C-star algebra being unital. The category of C-star algebras, well, I haven't described it very well because I didn't tell you what kind of morphisms I'm using, but with unital C-star algebras, I will be using unital star homomorphisms, and that's it. In general, of course, I have my ideas about what the right, not proper, but right notion of morphism is. Okay, so we're looking at the category of unital C-star algebras, and with every unital C-star algebra, there is like the same object really, but of the dual category. So in order to emphasize this, we will really use notation like this bold X or bold G for objects that correspond to C-star algebras C of X and C of G. And of course, the main point is that C of X and C of G absolutely do not have to be commutative. They just look like this on the page, but they are just some unital C-star algebras. Okay, so here's the definition of a compact quantum group. So let's maybe quickly go through it. So we have a compact quantum space. So there is a unital C-star algebra C of G. And just like a group is equipped with a multiplication, which is a two-element operation, so a map from the Cartesian square of the group to itself. Here we are given a co-multiplication, which is a unital star homomorphism from C of G to the tensor square of C of G. And since these are arbitrary unital C-star algebras, one should specify which tensor product we are using. So we are using the minimal tensor product always. There is a possibility to develop the theory, for example, with the maximal tensor product and other versions, but really this is the basic and most used idea. So the tensor product is just the minimal tensor product. And okay, associativity of group multiplication is encoded in this co-associativity condition here. And the fact that we are dealing with a group, not a semi-group, for example, is encoded in the fact that these two sets, so this one and this one, these two sets are linearly dense. So they span a dense subspace of the tensor product. The tensor product is already completed. So those of you who are acquainted with Hopf algebras will certainly know that with Hopf algebras, the spans of these two sets are just equal to the tensor square of the Hopf algebra. Here we are dealing with a more functional analytic approach, and everything needs to be completed and so on. So these spans are dense. And so this is a compact quantum group, and this definition, although it's very compact and beautiful, it doesn't quite reveal how rich the theory is. So I will, well, tell you a little bit about this theory, but we will start with, well, one has to start with this example. This is absolutely crucial. So the quantum SU2 denoted this way. The Q is a number between -1 and 1, but not 0. And we define the quantum space SUQ2 by defining the C-star algebra. And the C-star algebra is the universal C-star algebra generated by two elements with a certain set of relations. And these relations are that this matrix is a unitary matrix. And we've already seen that as well. I don't remember at which talk, but that was already mentioned. So if you recall what SU2 is, the group of unitary 2x2 matrices with that determinant 1, you will then remember that these matrices always have this form alpha, gamma bar, alpha bar, where alpha and gamma are complex numbers whose sum of squares of absolute values is 1, which is the determinant of the matrix. So here, well, this is almost the same. It's just that there is this Q over here. Right? That's the whole difference. And now alpha and gamma are something like coordinate functions on our quantum space SU2. Okay, so this is the space. And now one checks that these two formulas actually do define a co-associative morphism, unital star homomorphism from this algebra to its tensor square. And well, if you look at it, this will come back in a second, actually. If you look at this formula, it's as if you wrote another such matrix here. Oh, that's very thick, but okay. If you wrote such a matrix over here and did matrix multiplication between these two, but put a tensor product instead of a product. So if you want to calculate the upper left corner of this product of matrices, you will have alpha tensor alpha minus Q gamma star tensor gamma, and that's what you get here. Okay, so there is no mystery about these formulas, and they're very nice. Okay. There is another example of a quantum space, the quantum torus. So the quantum torus is, well, the two torus, there are, of course, higher dimensional tori. And okay, I don't want to go into all this because there's a whole zoo of quantum spaces. Anyway, this is probably the best studied quantum space ever, and it's corresponds to the C-star algebra generated by two unitary elements which do not commute, but they commute up to this constant e to I theta. Theta is a real number, or well, between 0 and 2 pi, or e to, sometimes it's written as e to 2 pi I theta, and theta is between 0 and 1. Anyway, the thing is that this famous quantum space does not admit the structure of a compact quantum group. Okay, if you go to the previous page, which I don't want to do right now, but can look at the definition, you would need on this quantum space a co-multiplication which satisfies these two density conditions, and such co-multiplication does not exist. Okay, so it was actually, on one hand, very interesting, on the other hand, somewhat surprising. After all, the torus is one of the more famous groups. But, well, there is actually, and this is very entertaining and interesting, that there is a quantum version of the double cover of it. It was first described by Piotr and Tetsuya Masuda. Very nice, rather easy example of a quantum group, but very interesting. Okay, so we are now in this situation. We have the notion of a quantum space. We have a notion of a quantum group. That's a quantum space endowed with additional structure. And some quantum spaces admit this structure, some don't. Okay, so the way to prove that a given quantum space cannot be a quantum group is to show that it cannot have all the other things that quantum groups have from that very simple definition there. So let me just list a few things that quantum groups have. So first of all, if we are given a compact quantum group, then there is the Haar measure. The Haar measure on this compact quantum group is a state. Of course, the Haar measure is a probability measure, so it has to be a state in the non-commutative world. And here is the description of the fact that it's the Haar measure, so it's invariant. If you write this out in a classical example, so when your G is an actual compact group and your C of G is then the commutative algebra of functions on this group, and H is the integral with respect to, well, some measure, then the invariance is precisely this. So there is the Haar measure. This is the theorem, one of the basic theorems of the theory. And since we are in the non-commutative situation, states can be traces or not. There is this distinction. And the name for groups whose quantum groups whose Haar measure is a trace is Katz type quantum groups. The more interesting ones are those that are not Katz type. Let me put it this way. Of course, they're all interesting, but Katz type is somehow a little less quantum.
So Piotr, can I ask a question? I recall that Katz type means the square of the antipode equal to 1. Is the same?
Yeah, that's all equivalent. Yes, and this is it will sort of come back a little bit. Various descriptions of that condition. Okay, so we have a C-star algebra. We have a state. Well, then there is the modular group. The modular group known from von Neumann algebra theory this is not something that C-star algebra theory really deals with, because the modular group usually only works on the von Neumann algebra level, but one can prove that for quantum groups, actually the modular group of the Haar measure defined in the GNS representation for the Haar measure actually restricts to a one parameter group of automorphisms of the C-star algebra. So it is, so here is this modular group, and here is some mysterious stuff that let me quickly describe. So it is given.
Sorry, Piotr, shouldn't it be delta
Yeah,
square?
it should be. Should be. I'm sorry. Sorry for all this. So this should be square. Can you see that? It will disappear with the next page. Okay, so the thing is that we know more than just that this group exists. It is actually, there is a formula for it in terms of a certain family of functionals, of characters, in fact, of this C-star algebra. Okay, so the fact that we have this formula actually will not be important, but the existence of this family is important. And there is also another one parameter group of automorphisms that actually looks sort of a little better, although there still should be a square. So we really have two groups of automorphisms. One is the modular group of the Haar state, and the other one is it's called the scaling group, and it's different, and it has its own very important role in the theory. Okay, so compact quantum groups actually come equipped with two commuting, which can actually be seen from these formulas, commuting groups of automorphisms. Okay, that's good. And now coming back to Francesco's remark, is that this condition of being Katz's type, well, it can be expressed with either group. Namely, I mean, if H is a trace, then the modular group is trivial. We know that. That's like the origin of the modular theory. That traces have trivial modular group. But also triviality of that other group is an equivalent condition to H being a trace. And the square of the antipode being one, and other ones. Okay, so this is a little glimpse into some elements of the theory. And let me continue that. Namely, groups also have representations, and quantum groups have representations too. And there is a very rich representation theory. And what is a representation? Sorry for this. A representation of a compact quantum group is a unitary matrix like this. So it's a matrix, n by n matrix over the C-star algebra, which can be written, of course, as a tensor product of scalar matrices times the C-star algebra, such that this formula holds. Okay, this is a unitary representation. I'm simplifying this whole thing a little bit, but that's what it boils down to. So we have a matrix with this property. And if you like follow the example of classical groups, then this really represents a matrix valued function, which has unitary values and is multiplicative. So that is a representation. Okay. For example, this defining matrix of SUQ2, so the one whose unitarity was really the part of the definition of SUQ2, is a unitary representation. Okay. So that is a thing that exists, and these elements of these matrices are called matrix elements of representations. So there will be a little bit more about that here. Namely, well, there are various notions of representation theory, like irreducibility. Irreducibility of a representation is that, well, it commutes only with trivial projections, 0 and 1. It doesn't commute with other projections. That's one of the ways to phrase irreducibility, and that works here as well. So the only projections in n by n matrices which commute with our unitary matrix in this sense are 0 and 1. So we have the notion of irreducibility, we have a notion of equivalence. So two representations U and V are equivalent if they can be intertwined by a unitary matrix U. That's again sort of direct repetition of what we have for groups. And since we have irreducibility and we have equivalence equivalence classes of irreducible representations. So okay, that's a long one here. So there is a name for the set of classes of irreducible representations. And in what follows, we will do what everyone in this theory always does. So with every class, you fix a representative. And this representative is a matrix, so it has matrix elements. And these matrix elements, now you should look directly here, sort of skip that part for a second. So what happens here? We are taking one matrix element, we're taking another one, star, taking a product and integrating over the group. This is like taking a scalar product of two functions in the L2 space. Okay, you see this. One function times the other bar, integrate. And we want, well, so think back to Piotr theorem, which tells you that matrix elements of irreducible representations give you an orthonormal basis after normalizing. So an orthogonal basis of the Hilbert space L2 of the group. So here, matrix elements of the representatives that we fixed should have scalar products delta Ki, delta Lj, so they really should be orthogonal. And now what classically you would have 1 over the dimension of the algebra, of the dimension of the representation. Here you have something else. You have some number and a trace of some diagonal matrix. Now, I don't want to go into the details of all that story, but thing is, Piotr theorem still holds for compact quantum groups, but orthogonality relations are not that simple. There is a certain matrix, positive matrix, strictly positive matrix, whose eigenvalues are listed here, and one can always arrange that it's diagonal, which are responsible for the scalar products and norms, basically, of different matrix elements. And if the group is Cutts type precisely when all these matrices are the unit matrix of appropriate size. This is another characterization. So I will leave this here, but these numbers rho alpha 1, rho alpha n, they will appear again, and they are related to the scalar products between matrix elements, and they are precisely non-trivial when our group is not Cutts type. Otherwise, they're just one, and you don't see.
You can do a quick exercise. So take the fundamental position of SUQ2. What would this matrix be?
Yeah, that would be, let me show that, that would be Q inverse or Q inverse Q, I don't remember.
Yeah, thank you. That's what I expected.
So if Q is not 1, then see that was a very good point. Okay. And the span of matrix elements of irreducible representations is dense in this C-star algebra C of G. So this is, again, like the Piotr theorem, that actually matrix elements span a dense subspace of C of G, and therefore they form a basis of L2. That's the same.
Piotr, can I ask Ludwig? Hi.
Sure. Yes, go ahead.
So in general, the determinant of this metric is rho alpha can be make 1 for SUQN.
Determinant.
So product of this rho 1 to rho n.
Let me just think a little bit. Yes, that is for SUQN, yes, okay. But the general story is somewhat complicated. We are used to the fact that eigenvalues of this matrix form a set which is invariant under taking inverse. So then the determinant is 1. But that is not always true. And Jacek Krajczuk, who is on Zoom here, has an interesting paper that, for example, proves this symmetry of eigenvalues with respect to taking inverses if the growth of the group is polynomial, for example.
Okay.
That means,
okay.
Very, very interesting things, but this is not always true. So for
okay, thank you.
Unitary, yeah. Okay.
But sorry, but if you multiply all the entries of the matrix by a scalar lambda, in the inner product, you have a lambda on top, lambda on bottom, and they simplify.
Yeah,
so
because
can you choose it? Yeah.
Yes. Okay. I told you I was not giving you the whole story. Okay. This matrix is fixed uniquely by asking that the trace of this matrix is equal to the trace of its inverse. Okay. I didn't do that. I didn't want to put everything on these slides. That's a longer story. But yes, this is precisely true. Okay, why is this not working? Oh. Oh, no. Okay, so now the quantum disk. What's the quantum disk? Well, this is it. This is a C-star. Well, the quantum space is described by a unital C-star algebra generated by one element with this relation where mu is a parameter between 0 and 1. And this was, as far as I was able to check, originally first mentioned by Shu. And then later there was a longer, much more substantial study of that by Klimek and Leszczynski. Okay, it turns out that this parameter mu is not important. The algebra is independent of the parameter, and it turns out to be isomorphic to the Toeplitz algebra, which is a graph algebra. I think I wrote that down here. Yes, yes. Here is the. So it is a graph algebra, and more importantly, I guess it fits into this exact sequence, where S here is sigma, is the symbol map. I didn't use sigma because of the use of the modular group before and later. So, okay, and let's assume that we have a compact quantum group, which is the quantum disk. So I would like to be rather precise here, and let's just keep not identifying things, but let's say we have an isomorphism I from C of G to this Toeplitz algebra. The Toeplitz algebra will be thought of as the algebra generated by the unilateral shift on little L2 of n, or Z plus, whoever prefers which notation, but anyway, this will be the Toeplitz algebra for me. And let's say we have this isomorphism. And the goal is to arrive at a contradiction after assuming we have such a compact quantum group. Okay, so we are assuming that there is such a compact quantum group G and this isomorphism pi. Of course, this isomorphism pi doesn't know anything about the co-multiplication. The Toeplitz algebra doesn't have any such structure, at least so far, right? So, okay, so first observations are that, and I will not go into the proof of that, but it's actually not very difficult. We can identify the family of these characters that were involved in the modular group and the scaling group. By the way, the word scaling is absolutely out of place here, because it only makes sense for non-compact quantum groups where we get an actual scaling of the Haar measure. Here we don't get any scaling of the Haar measure, but it's still called a scaling. It leaves the Haar measure invariant, but so we can identify these characters pretty much because these are the only ones available. So what are the characters of the Toeplitz algebra? Well, you can only go to this functions on the circle and evaluate. These are the only possibilities. And so I will not go into the proof of that, but there is another thing, namely this shows, although this can be seen independently, that this hypothetical compact quantum group G, that is isomorphism to the Toeplitz algebra, is not of Katz's type. It is not of Katz's type. It has non-trivial characters. These characters would be trivial if it were of Katz's type. Also, there are no faithful traces on the Toeplitz algebra. So, yeah, that is not this group is certainly not of Katz's type. Now, here is something worth our attention for a little bit, namely, let's look at a matrix element of an irreducible representation. And let's put it in this B of this H is the little L2, using our representation pi, our isomorphism pi. So this image is compact if it's off diagonal, and it's Fredholm if it's diagonal. Now, I guess everyone knows what a compact operator is. A Fredholm operator is one with finite dimensional kernel and poker. And this proposition is really directly like the consequence of the previous one, because to be compact is to be in the kernel of the symbol, and that's how we do it. Okay, and then to be Fredholm means to be invertible after dividing by the compact. So that's once. And also we need to know things, what this the modular group and the scaling group, what they do to matrix elements of the reducible representations. I left that out, but this is no. We know how they.
Piotr, so for you, the Toeplitz algebra is already bounded operators. And
Yes, it's represented all the time. Yes, it is.
By this unilateral shift standard.
Yes, this is. Yeah, this is the usual way.
Yeah. Okay. Thank you.
Okay, so here is the stuff. This is a Fredholm operator if I is equal to j. That's the important. Now, something more. Let's take the Haar measure on C of G. Let's use the isomorphism to transfer this functional, the state, to the Toeplitz algebra, and then let's restrict it to the compacts. This gives us a state on the compacts. A state on the compacts is given by a trace class operator and the trace. Okay, that's always like this. So there exists a certain trace class operator such that this restriction is the trace with this density matrix. And also one can prove that the kernel of A has to be 0 because that state has to be. And anyway, so we have this trace class operator A. One can prove that this A implements the modular group when moved over to from C of G to the Toeplitz algebra by our isomorphism. Okay, so you go from go from the Toeplitz pi inverse to C of G, then act with the modular group, take pi back. That is just implemented by this operator A, implemented in this sense, right? In the sense of functional calculus. Okay, so these are rather simple things. Next, this is absolutely not that simple. There exists a positive self-adjoint operator B on this Hilbert space that implements similarly the scaling group. The modular group was implemented by A. The scaling group is implemented by something else. Now that is based on a difficult and important theorem of Kalman about automorphisms group, implementation of automorphism groups on von Neumann algebras that start on a C-star algebra. That is not an easy theorem, but this holds. And notice that I wrote positive self-adjoint. So that means that I'm not assuming that B is a bounded operator. Positive bounded operators are self-adjoint. This one possibly is unbound. Okay, but it's strictly positive, so we can take these functions B to the IT. Okay, and these two operators, A and B, they commute. They strongly commute, which means that all bounded functions of both. I mean, one is bounded already, but they commute in the strong sense. Okay, so
But A is bounded, right?
yes, A is bounded. A is in fact trace class, which is important. Okay, so before we proceed, there will be one slide sort of just advertising certain kind of notation. So please try to remember where we are and just let's do it like this. If we have a self-adjoint operator, bounded or unbounded, on a Hilbert space H, then instead of writing the kernel of T times 1 minus T, we will just write that. The subspace where big T is equal to little t, okay? That's the spectral subspace. That's a very convenient notation. Oh, yeah, what is that? That is crazy. I have no idea what that means.
Copy and paste.
That is just like, it's not even there. It's,
Doesn't belong there, yes.
sorry, I'm not sure. I don't know how that got. Just okay, let's go back to this. This is the eigenspace where big T is equal to that number. Okay, and the projection, well, this will be the notation for the projection onto this subspace. Why? Because if this bold chi here means a logical evaluation of a proposition, which is 0 or 1, depending on whether the proposition is true or false. And when the proposition depends on a parameter, a real parameter here, then this becomes a function which you apply to the operator. So this is actually very consistent to write it this way. Okay, it is a function applied to the operator, and this function is just here. Okay, the logical evaluation whether little s is equal to t or not. So once again, this is a notation for an eigenspace. This is a notation for the projection onto this eigenspace. Also, I mean, this notation is, it's like in probability when you write probability of a random variable x equal 5, right? And that's what you write. So this is very, very much like this, and makes sense even. Okay. So this will be our notation. Now we're going back. We have these two operators, A and B, that implement the modular group and the scaling. Okay. Now, A is trace class. So that means its spectrum consists of eigenvalues. It has a complete set of eigenvalues, and they're all finite dimensional. So our Hilbert space splits into a direct sum of eigenspaces of A over the spectrum, and actually the kernel of A is 0. So the eigenspace for Q equals 0 is 0. And all the other ones are finite dimensional. Okay. And yeah, which is written here, sorry for it. And then also we know that B commutes with A. So it really can be written as such a direct sum in this on this Hilbert space, a direct sum of such reductions. Okay, we are reducing B by this eigenprojection of A, and this is equal. This follows from the fact that the two operators commute. And I will use this notation BQ for this reduction. Okay, so BQ is B restricted to the eigenspace A equal Q. Okay. So this is just notation. And here is a proposition. If we take a matrix element of an irreducible representation, use pi to put it into the Toeplitz algebra, then when it acts on an eigenspace of A, it moves it to another eigenspace of A, and the other eigenspace is, well, it differs that so that the eigenvalue becomes multiplied by, you see, this was the part of that diagonal matrix at the beginning. Okay, so this thing, and the way we prove that is because we know what the scaling group and the modular group do with these matrix elements. This is how we arrive at this. Okay. And the other thing is that these operators pi of u alpha I, so the diagonal elements, they move. Well, they move. What did I write here? Oh, this was supposed to be H. Yeah, this was supposed to be H. Sorry. I think. Yeah. They also move the spectral subspaces of these restricted parts of the operator B. Okay, so here you take a number lambda in the spectrum, and the spectral subspace under the action of this operator gets moved to this spectral subspace. Okay, this is, and the technique of proof is also based on how these two groups act on matrix elements of the reducible representation. So we have these two facts, and now we'll use them for this theorem, that the collection of all eigenvalues of all these BQ operators, remember, BQ was a restriction of this B, which was possibly even unbounded, but to a finite dimensional subspace. So there are just eigenvalues there. There is no continuous spectrum, anything like this. So BQ is just a matrix, an operator in a finite dimensional subspace. So the set of all these eigenvalues over all restrictions is finite. That's the thing. How do we do that? We do it like this. The first part of the proposition from the previous slide lets us write the kernel of such an operator, pi of u alpha I, as the direct sum of its intersection with all eigenspaces of A. Well, this is because this operator moves each eigenspace to an orthogonal one. So if this operator kills a vector, it has to kill every component in every eigenspace of A. And knowing that, we recall that this is a Fredholm operator. Its kernel is finite dimension. Well, that means that these subspaces, only finitely many of them can be non-zero, right? Because the kernel has to be finite dimensional, and we know that it can be written like this. So, this sum has to be a sum of mostly zeros, just finite number of non-zero subspaces. Okay, so this means that there exists a Q0 such that for every Q below Q0, this operator is injective on this on this eigenspace, just because this sum has to be really finite. Okay, and the Q's go from somewhere, from the norm of A down to 0. There are infinitely many of them. So if only finitely many contribute to this kernel, then they have to stop contributing at some Q0. Okay, so we know that. Now, here is another part that I will have to sort of skip. But the point is that G being not of Katz's type, as I said, is equivalent to the matrix, the row matrix being non-trivial, at least for some alpha. Non-trivial means that it has a strictly greater than 1 eigenvalues, because the trace of this matrix is equal to the trace of its inverse. So some eigenvalue has to be strictly greater than 1. So we choose that situation. Okay, we choose that alpha and that pi such that this holds. Okay, and now let's assume that we have an element of this set that comes from the part with Q only smaller than Q0. Okay, so we have these Q, they start at some maximal Q at the norm of A. They go down, then there is this Q0 that was finitely many only. And then there is infinitely many below. By the way, I should be showing it in this direction. So there is a Q0 and there's infinitely many Qs below, just finitely many above. And I claim that only the above actually show up in this part. So let's take an element that comes from below Q0. So let's take a lambda that's in, you see, that's from somewhere below Q0, which means that there is some Q tilde smaller than Q0, such that lambda is in this spectrum. Oh, let's take that. By 2, if we take, again, this was supposed to be H. I'm so sorry. H. If we take an element of the eigenspace for this eigenvalue, that there is a non-zero vector, it's an eigenvalue after all, and we keep hitting it with pi alpha I, it keeps getting to another eigenspace with a larger eigenvalue, because rho alpha I is strictly bigger than 1. So we keep it kicking it to an eigenspace with a bigger and bigger eigenvalue, and each time by the same amount. So that goes to infinity, right? I mean, okay, but that means that at one point it is below Q0, and then the next iteration it is already Q0 or more, right? Since it goes to infinity, that has to go over Q0. And then you write something like this. This here is really the nth power of pi alpha II acting on psi, right? So the nth power gives us, moves it to this. You see here we have n, 2 times n, and that's already bigger or equal to Q0. So this, I'm sorry, this was always copy paste. This H, the eigenspace has to be 0 because lambda is not an eigenvalue. This is how we chose lambda. It's not an eigenvalue of BQ for Q bigger or equal Q0. It is an eigenvalue of BQ for some Q strictly smaller than 0 and not bigger. So this is 0. So the nth power does this, but the nth power of that operator acting on psi is this operator acting on this part. And it gives 0. But this was supposed to be injective. This was supposed to be injective on these eigenspaces below Q0. And that is a, well, okay. That means that B has to be a bounded operator because the spectrum of B is finite. It has to be a bounded operator. And now that is a nuisance because you have to use a certain rather not very well written up in literature results that if B is bounded, then the scaling group is trivial and B is trivial and it's custom. Okay, that's the part. I mean, it is written down, but there is, I don't think there is actually a theorem. It's just as a remark in a book or something, but it is true. It does hold that, yes. So here we are. This is the contradiction. Our G had to be not of Katz's type because there are no faithful traces on the Toeplitz algebra, or there are other reasons. But then it has to be a contradiction, which means that such a G could not exist in the first place. Okay, so this is the end of the story for the quantum disk. The quantum disk is not a quantum group. This, okay. The way we proved this looked, well, like an exercise in all these, shifting eigenspaces of one operator by another and so on. True, yes. But one could try to make more general sense of it, see if this technique has more applications and so on. It is not easy. I don't have like absolutely general theorems, but at one point, first of all, Alexandru Kirvasitu joined Jacek and myself and added some insight into this. And then we were able to sort of extend this technique in other situations as well. So let me go to some remarks about this. Namely, this is the theorem we have with Jacek and Alexandru. This is in a paper titled Type 1. Well, I don't remember exactly the title, which is probably strange, but it's about quantum group structures on type 1 C-star algebras. But it's not a theorem for general type 1 C-star algebras, just for such algebras like here. This is, of course, G is then, C of G is then type 1. So if we have a C-star algebra, unital C-star algebra C of G that fits into an exact sequence with a commutative algebra here. So this X is not this blackboard bold, it's just a regular X, so a compact space X. And here, quite crucially, is a finite direct sum of compact operators on different Hilbert spaces. So these HIs could be finite dimensional or whatever. Then one can prove that, well, it could still be a quantum group, but it would have to be a finite quantum group, which would mean that it's a finite dimensional C-star algebra. So basically not interesting. I mean, I guess finite quantum groups are just finite dimensional Hopf algebras with additional properties. So they are well known, I guess, or well studied. So here is, and well, that in particular gives us the generic Podlish spheres. That was where I failed miserably when I tried to do it before, because I was able to prove that the quotient Podlish sphere doesn't have a quantum group structure, but then the generic one, for which you have k plus k, I guess here, is well, I originally thought that maybe there had to be some strong connection between the quantum group structure and the graph algebra structure. Even though one doesn't assume that at all, it would somehow have to follow. Somehow, I don't know, the gauge group would have to be one of those two groups or something. And yeah, in examples, it's like this, but I was not able to use this to disprove existence of the quantum group structure in these cases. Had to use some other techniques with great help of Jacek Krajczuk. And anyway, by now we know that Podlish spheres do not carry a compact quantum group structure. Also, that was already done way before this. Other kinds of like Matsumoto spheres, and there are other, I already, unfortunately, this was like 13 years ago or something like this, and I forgot the names of these quantum spaces, but one can exclude many families of quantum spheres from the world of quantum groups. They do not carry quantum group structure. Okay, and so let me go to my really final slide, which is what happens on von Neumann algebra level. So let me quickly, that this is doesn't do justice, this theory, but one can take this Haar state and perform GNS construction, and then we get a representation of our C of G on a Hilbert space, which is of course called L2 of G. Clearly, this is the Hilbert space L2 of the group, the quantum group, and then you can take the bicommutance or the strong closure of your image of the GNS representation. You get a von Neumann algebra. This is called L infinity of G, and this is an interesting von Neumann algebra. Let me maybe, before putting on the next remark here, let me say that if our quantum group is so-called dual of a classical discrete group, which means that C of G is the group on a group C-star algebra of a discrete group. So you get a unital C-star algebra, and then L infinity is the von Neumann algebra of that group. Then it has a trace, the von Neumann trace. It always has a trace, and so you get type 2 algebras. You can get a factor or not a factor, but you get type 2. You never get type 3 in this case, right? But with quantum groups, we will be able to take type 3, and you will not be able to get type 1. So these are the results with Jacek again. And first thing is that a type 1 factor cannot be L infinity of a compact quantum group unless it's C, unless it's a trivial group and it's classical. But it cannot happen. Even more is true. L infinity of G cannot have an infinite dimensional type 1 factor, so a B of H for an infinite dimensional H as a direct summand. It just cannot happen. And here is the thing that we are most proud of, I guess, in this story, that we can construct quantum groups such that you get all injective type 3 lambda factors. This is written for lambda strictly greater than 0. So of course, well, the classification of von Neumann algebras, of injective von Neumann algebras, tells us that there are these special factors, and there is only one for each lambda, and all type 3 factors are either that or type 3, 0, which there is still space here for 3, 0. So in fact, you can get the same type 3 lambda factor for an uncountable family of pairwise non-isomorphic compact quantum groups. So they are different spaces. I mean, there could be the same spaces. I didn't check. They are different quantum groups, so they're not isomorphic with the co-multiplication. Okay, but the von Neumann completion is the same, and it is a type 3 factor. And also for 3-0, we have a result that's quite satisfying. The 3-0 factors are crazy because there's very many of them. For 3 lambda with lambda bigger than 0, you have 1 for each lambda. And 3-0, there is a whole, they are classified by certain flows. And we have at least uncountably many of those. We have uncountably many different 3-0 factors S L infinity of some compact quantum group. So this is, and this I think is, yes, this is the last thing I wanted to tell you. And by the way, these things in a way also involve the way the scaling and the modular group act on matrix elements and how spectral subspaces get shifted around in a more involved way. Okay, thank you very much. Oh, I see. Oh, then I thought there was a question here, but this is clapping as well, so thank you very much.
Other questions?
Oh, Piotr, 2 slides back when you had this exact sequence, remind me.
Yes.
Yeah, this one. So, do you know what the index map in K-theory is in these examples?
Well, people know that for specific examples, but in general, no, I didn't check, and it would involve me getting into a book and learning about K-theory again.
No, because it seems to me that, well, there's only one example I've seen where the index map is trivial. And in that case, the algebras you get with non-trivial index seem to be very different. And I think that's an interesting question. But I just wonder if this would be evidence that the index map should be trivial when you get this from a.
I don't know, but perhaps this might be an important point to see if some very geometric or I guess topological properties could be used for this. What we did was something completely different approach. We somehow are not geometers even in this non-commutative. We just have to get to eigenspaces and operators. But so that's all I can. I simply am not an expert.
Yes, okay, so I have 2 questions. For the non-commutative torus, I guess is very different. The way you prove is,
Yeah.
but
Yes,
who did it? Do you have a reference?
yeah. So I have a paper that's, I think, 2010 in Proceedings of the AMS, and there I also wrote up these results and some additions in Proceedings from Banach algebras here in Bangladesh years ago.
And yeah, and what about the classical case? For the closed disk, what can you say?
It's trivial.
Why is it trivial?
The fact that it's not a group, because in a group, the topology, the structure of neighborhoods around every point has to be the same. And if you take a boundary point and a neighborhood of that point, if you remove that point, you can have a neighborhood such that if you remove the point, it's still.
So you
simply
cannot never
connected
have a
and-
boundary, basically, you're saying, yeah. And also for the sphere, I mean, to prove that is not a Lie group is easy, but what about the topological?
Well, then the one I heard was the standard would be to look at the Hopf algebra structure in the homology ring, the integral homology ring, but I don't know. I'm not versed well enough in all those homology theories in non-commutative geometry. I tried with K-theory, like what would the co-multiplication induce on K-theory, but nothing came out of it. And the K-theory of these algebras in examples pretty simple. I mean, these are not complicated groups, and somehow I couldn't see how to use that. But, you know, I'm not a geometer, really.
Let me follow up just a second to Francesco's question. It is very well known, it's a theorem from the 70s, that the only compact Hausdorff topological group which is contractible as a space is the trivial group. So in particular, the classical disk is immediately excluded. But I believe when I asked this question to Jacek Krajczak ages ago at our North Atlantic seminar, if you can use the fact that we know, oh, sorry, yes, actually, I take it back. The thing is that, for instance, quantum disk is not contractible. Oh, yeah, and you can very easily see it because there are projections in fact. Okay.
Oh, okay.
So there's a very nice, simple argument that shows that it's not contractible.
The inside becomes sort of
Fragmented.
disconnected.
Yeah, exactly. Yes, exactly. So the quantum disk is not contractible. So the classical argument, which prevents the classical disk from being quantum group because it's contractible, does not apply. Yet you have a completely different reason for it not being quantum.
Do you have a sense of whether you should be able to get every 3-0 factor in this way?
That is a very good question. I don't know. I mean, the way we are doing this is somehow we just guessed a certain procedure, and we're able to compute the T invariant and the S invariant. And that means that we are not even close to seeing where these examples fit in the classification. We don't have their representation as cross products. We would like to do that. I haven't had, say, the time and energy to do it, but yeah, we should check. This is, yeah, Stefan Vass also gave some suggestions as to how to go about this, because these constructions that we do are really close to, they are infinite tensor product constructions. They are just not infinite tensor products of finite type 1 factors. They are infinite tensor products of infinite type 1. These theorems that you can find in old papers on infinite tensor products, they usually are not, at least explicitly, they do not let you put infinite factors there. So I'm not sure how to use these theorems really. But this is a very good question and something we did think about looking into. Haven't looked at.
If I may comment on that.
Yeah.
Can you hear me well?
Yes, we can. Yeah.
Thanks. So maybe just a comment about this type 3 factor that we obtain. One thing that is clear is that we don't get all of them because we only get ITPFI factors, actually ITPFI2 factors. And there are type 3-0 factors which are not in this class. So one thing that is clear is that we get a strictly smaller family of factors.
Oh, okay. So even though our factors are infinite, then what we get is really only the same thing that you would get from finite type 1 factors, right? I didn't somehow.
Yeah, I think Stefan Weiss gave us an argument, but still it's not clear whether we get all of them. When you try to get in this invariant, it gets
okay.
kind of messy.
Yeah, okay. Yes, I agree now. Thanks.
Are there examples of compact quantum group like that matrix algebras are like in the sum end of L infinity, not like I. So if said that I infinity is not there, 1 infinity type, or it is always it is like it need not be a factor, but matrix algebra, can it be in the sum end part like finite dimensional?
So you mean like an infinite direct sum of finite dimensional? With that, if you do that, that's either not unital or what?
It need not be infinite direct sum. It could be just like
finite direct sum of finite size matrices. Yeah, well, every finite quantum group is exactly of that form.
okay, but like other example where like the compact quantum group is not this small. You take L infinity. So I'm just looking for some example in which does not fit in that example, like in first and second case. So in first you have type 1 factor.
Yeah, so B of H.
Yeah. And in the second you have that
B of H plus something.
Yeah, but I'm just looking like it's
Can you have like matrices
Yeah.
plus something? Well, you can already have it in the finite case, so can you have it in I didn't think about this. So can you have like a matrix part and then something continuous? I don't know. One would have to check. I mean, that should not be a difficult question, but I don't know immediately.
And like other example of non-injective factor of type 3.
Well, yes, and one can just take the tensor product of this von-Neumann algebra with group von-Neumann algebra of a non-amenable group, right? So which would correspond to taking a Cartesian product of our quantum group with a dual of a classical group, so another quantum group. And then you get non-injective, yes. But with non-injective, the thing is that there is so far no classification. So we wanted to have the classification. We wanted to stick with injective.
So I have a very vague kind of question. So when you were looking at the graph algebra structure, were there any indications that you can have quantum group structure for graph algebras? Because so looking from your talk, so Toeplitz algebra, which is a graph algebra, is not, and then the generic Podlesh is also a graph system algebra, and it's not, it doesn't have this quantum group structure. And we only have this SU2, right?
Yeah.
So are there any indication that when you were looking at any connections between the graph structure and the quantum group structure?
Well, the point is I couldn't find any connection between the two structures. So if I assumed having both and wasn't any more clever after this assumption. So I don't know. I mean, it is funny that, yeah, quantum SU2 is a graph algebra, although that presentation with the two loops and all that, yeah. So that is precisely related to Q equals 0 when one of those density conditions fails. So the thing is that Q equals 0 gives an isomorphic C-star algebra, but that particular presentation is not well adapted to quantum groups, because if you write the formula for the co-multiplication, it actually is not a quantum group, it's a quantum semigroup. So going back, somehow this Q different from 0, it's as if this graph algebra structure was a little misaligned. I don't know if the word is correct. It just happens that for all different Qs, the C-star algebras are the same. But only when Q is 0, the graph algebra structure can be, well, it's not difficult to see that the relations can be written as graph algebra relations.
Mm-hmm.
They're not directly the same, I think, but they're close. There is a partial isometry there and so on. And when you put a Q different from 0, then I'm not even sure how, I mean, the passage to graph algebra relations is nonlinear and difficult.
Yes. Okay,
But this was a good question, because you look at the graphs of SUQ2, Toeplitz, Podlesh, and they are graphs of the same type. I mean, you cannot really say, okay, maybe there's no single, but they're all, you know, finite graphs, just some loops, some edges, few vertices. And I'm wondering if it's possible by looking at the graph. Okay, I would assume that with probability, I don't know, 99.9%, it will not be a quantum group. But I would be nice to see that there are some immediate no-goes. You look at the graph C-star algebra for a given graph. Oh, if it's such a graph, it's definitely.
Well, it would be even nice to understand if there is a one which is not SUQ2 or the circle. If there is a third example.
Yes.
Oh.
Yeah,
Well, well, it will take someone with more knowledge than myself, I guess, well, to answer. Maybe in the future it will be easy to say, well, the co-multiplication to be nice, it requires the graph to do it, but no idea how that would. As I said, I tried through K-theory and somehow it, I mean, I did compute the whatever is induced on K-theory and it just gave me nothing. I mean, it was like, I don't know, identity or something.
Thanks. So I was just curious, like that also like that second result, like that you mentioned, like with the summons, can you explain maybe like why, like for layman, kind of quantum group layman, I'm like just knowing the definition, okay, co-multiplication, like why there can't be such a summon, like
Well, okay, so basically, that's how it goes. First, let me address point one and then try to tell you how that works with the second one. So here we keep at the same game. We have the set of matrix elements that spans a dense subalgebra of the cell infinity. And we know that both commuting groups of automorphisms multiply them by these matrix elements by certain number related to those row numbers. Okay, so we know that. And then we can look at the operators that implement the groups, they commute, and then they shift their respective spectral subspaces in ways that imply that the group has to be Kac type, but it cannot because there are no faithful traces on B of it. Right? So that's, and then the second part is really just tweaking this argument. So you have this summoned and you show that the summoned has to be preserved by the two groups. And then again, this, and then the R measure would have to restrict to a faithful state on this B of H. And so it's really the same argument. So this summoned, if it exists, it has to be somehow preserved by the structure, by these two groups in particular. That's the most important. That's how it works.
so basically boiled down like there is no traces on B of H.
Yes. Yeah.
Thanks.
No more questions? Then maybe I have one very quick. It's well known that classical disk is a monoid. Okay, it's well known that usual two-dimensional sphere is almost like a group. There's only one pair of elements where this multiplication is not well defined. It's 0 and infinity. Okay, so did you consider the question whether quantum versions are similar? There are monoids, there are almost groups or partially defined groups.
Well, no, okay, so the short answer is not in this work. I mean, yeah, well, the Toeplitz algebra is a monoid, a quantum semi-group, of course, in a sense. There is a paper on that. I didn't study it because already somebody wrote about this. So I guess I didn't go into these things, no. And by the way, removing a point or 2 points or something like this puts you in the world of non-compact quantum spaces and quantum, well, groups and semi-groups and so on, which is very interesting and I guess a good place to look.
But my question was not about removing points.
Well, but you said
partial
that
structure.
Oh, a partial structure.
Almost everywhere defined.
Okay, I didn't look into this. There are papers with titles like partial quantum groups. So, but I didn't look into.
Okay, so
I have one quick comment, if I may, just because it's a conference about graph algebra. So you showed this non-commutative torus at one of your starting slides, and where it is not a quantum group, but if you, it's also not the usual graph sister algebra, but the classical torus is a rank 2 graph sister algebra, And when you go to higher and graph sister algebras, you can have twisted higher and graph sister algebras. And then such with quantum torus is a twisted graph algebra. So that-
Well, higher rank, by the way, I mean, quantum groups, many quantum groups are higher rank.
Yes,
graph
like
algebras.
SQN,
This-
yes.
Yes,
Yeah,
this
like
is
SQN.
your recent.
just a comment.
Okay, thank you very much. If there are no more questions, thank the speaker again.
I think that there is a question
And
from
I have-
Professor Jackowski. He's raising hand.
Yes,
Oh.
Yes, please.
hello. So first of all, I regret I had to leave the conference in person, but still I can attend online sometimes. My question is from topologist's perspective. You know, there is the famous theorem that the only spheres which admit some kind of multiplication is S1, S3, and S7. Does this fact has any interpretation in terms of algebras? And is it true that, you know, that the multiplication at the level of the algebra exists, if and only if it exists at the level of topological spaces? Well, how these things are related? Perhaps you can give a different proof for S1, S3, and S7 in terms of algebras.
Well, I can say certainly that the existence of the co-multiplication, which is co-associative, is equivalent to having an associative multiplication. These density conditions then are in the compact case equivalent to this multiplication being a group multiplication, so existence of inverses on the unit. Otherwise, I mean, I would be surprised if I could prove these classical theorems in some new way using.
But do they have some implications in the theory of C-star algebras?
I would rather say that these are results on quantum groups. C-star algebras, I don't know. I mean, perhaps because there are, after all, having this co-multiplication gives some additional structure. You can then induce, as I said, on K theory, some maps and things like this. But I don't think of my results as results on C-star algebras. They are very particular to quantum groups. After all, I used very strong quantum group results. So yeah, this is not, I think, a general C-star algebra result applicable to some other situation.
And if I could comment, this density problem is about, in the classical language, is about cancellation.
Cancellation.
Yeah, so everything is based on very well-known classical theorem that if you have a semi-group which is compact and satisfies cancellation, it must be automatically a compact group. Great.
Thank you.
Thank you. This is all. Oh. Well. Okay. So please, people interested in